A cantilever beam has a cross section of an isosceles triangle. Base is equal to 1 meter and height is equal to 1 meter is loaded as shown in figure. We have a fixed support at A and at free end we have couple is applied equal to 3 kilonewton meter. The maximum tensile bending stress we have to find out. He says that a tensile. It means that we have to first check that whether this bending moment is positive or negative. If we have a 3 kilonewton meter is a clockwise moment at A and B. So same reaction you will get at A. So this one is a bending moment M. In this case we have a case of hogging. And in case of hogging you have to treat the value of M as a negative. So we have value of M is negative 3 kilonewton meter. The vertical axis, which is a symmetry axis passing through apex. And the centroid will lie from the base at a distance equal to h by 3. So this one is representing the centroid position G. And here we have the vertical distance for the top fiber is a positive value. Let's say this distance is equal to y is h by 3. H by 3 is same as equal to 1 by 3 meter. As far as the bending moment is considered, it's a negative value. The moment of inertia about the z-axis is a horizontal this time, and the vertical axis will be equal to y-axis. So for top fiber, we have y value is positive. So we have a maximum bending stress at top fiber will be equal to minus m multiplied by y for the top. So y is positive here, m is negative, negative become positive, divided by the moment of inertia about the z-axis. So we have minus m, which is equal to minus 3 into 10 to the power 6. Value of y is 1 by 3, so we have to multiply by 1 and divided by 3. And the value of Iz is given is 1 divided by 36. 1 by 3 is meter, so you have to multiply by 1000. And this value of 1 by 36 is meter to the power 4. 1 meter is 10 to the power 3 and power is 4. So you have to solve this and you have to find out the maximum value of a bending stress. Negative become positive. So you will get this value as a positive value is positive 36 will be megapascal. And since positive, it's a tension. A cantilever beam with a triangular cross section. So this time all this problem will take either of triangular section or circular section. So cantilever beam with a triangular cross section carries a uniformly distributed load of intensity W equal to 2 kilonewton per meter over the entire length. The depth of the cross section is twice is the base. So base is B, then the depth is H, and this value of H will be same as equal to 2 times of base. Apex is below the base, so right now the apex is below the base. Allowable tensile and the compressive stresses both are equal to 24 megapascal. The minimum value of the depth H we have to calculate. H value we have to calculate, and we have given the length, that is the span length is given. So we have span length is L is equal to 2 meter. Whenever we have given the cantilever beam, then the maximum bending moment will be always at the fixed end, that is at point A. To find out that maximum bending moment, we'll convert the UDL into equivalent point load. So let's say we have uniformly distributed load is represented by W. We have length equal to L. So total equivalent point load is W into L. That will exactly act at the halfway. Halfway means L by 2. So this load is same as W into L is 2 multiplied by 2. That will be equal to 4 kilonewton. And this point load will act at L by 2, that will be equal to 2 by 2 is equal to 1 meter. So using this equivalent point load, very quickly we can calculate the bending moment at point A. So maximum bending moment will be at point A, that will be equal to W into L by 2. L by 2 is same as equal to 1 meter. So we have W into L is equal to 4, L by 2 is equal to 1. So maximum bending moment will come out to be 4 kilonewton meter. Axis of symmetry for the given figure will lie through a vertical line passing through the apex. So centroid will lie on this vertical line, and from the base it will be equal to h by 3, and from the apex it will be equal to 2h by 3. So this was the position of the centroid, that equal to G. Top fiber here at distance equal to h by 3, and the bottom fiber at distance equal to 2h by 3. This one is the horizontal axis is Z and the vertical axis is Y. Now the bottom fiber here is at a maximum distance from the neutral axis. So this one is same as neutral axis. So this value of 2h by 3 will treat as a C. Indicate here the maximum distance of the bottom and top fiber from the neutral axis. So we know the value of MA, we know the value of C, maximum stress is known, that equal to 24. So we'll use this value, and this value will be at the bottom fiber. So maximum value of a bending stress sigma B maximum is same as equal to the maximum bending moment, that equal to MA multiplied by C divided by I. Maximum bending moment is 4. So we have 4 into 10 to the power 6. Value of C is same as 2h by 3, 2h by 3. And the bending moment is BH cube, B into H cube divided by 36. So 36 will shift in numerator. Here we can substitute for B also. We have B is same as equal to H divided by 2. And directly we'll get our answer in H. So this 3 and this 36. So 12 is left in the numerator. So we have 4 into 2, 8. 8 into 12 is 96. So we have 96 into 10 to the power 6. We have H, and this is H cube. So 1 H square is left. And the B is same as H by 2. So it is again multiplied by H, and 2 will shift in numerator. On the left hand side we have maximum value of bending stress. 2 into 96 is 192. Maximum bending stress is same as equal to 24. So we have 24. 96 into 2 is 192 into 10 to the power 6 divided by H cube. I have to solve this. So you will get the value of H is approximately equal to 200 mm. So required value is, minimum value is H equal to 200 mm. Any value greater than 200, the bending stress will be less than 24 megapascal. A simply supported beam of span 6 meter and 75 mm diameter carries a uniformly distributed load of 1.5 kilonewton per meter. What is the maximum value of bending moment and what is the maximum value of bending stress? We have to find out. This time the section is changed and we have a circular cross section. We have given here simply supported beam, span equal to 6 meter, diameter of the circular cross section is 75 mm. So we have a span is equal to 6 meter and we have UDL is equal to 1.5 kilonewton per meter. Now number of problems already we have solved in the case of UDL on a simply supported beam, and already we have proved that the maximum value of a bending moment for a UDL on a simply supported beam is equal to W into L square divided by 8. So in this case we have W is same as equal to 1.5, length will be equal to 6 square divided by 8. So in this case the maximum bending moment, since we have used the end formula here, already we have proved this formula, this come out to be 6.75 will be kilonewton meter. That is the first part. We have given here the cross section is a circular with a diameter D is equal to 75 mm. In case of circular cross section, that equal to G. We have a horizontal axis is Z and the vertical axis is Y. The top fiber here and the bottom fiber here is at the same distance. So we have value of C is same as diameter divided by 2. Here also value of C is equal to diameter divided by 2. Moment of inertia is pi by 64 d to the power 4. So maximum bending stress can be occur either at top fiber or bottom fiber. We are only interested in the maximum. So maximum bending stress is given as the maximum value of a bending moment multiplied by C divided by I, that is IZ. So in this case, the maximum bending moment is 6.75 into 10 to the power 6. That will be Newton mm. And the value of C is d by 2. D by 2 is 75 divided by 2. Moment of inertia is pi by 64. So 64 will write in numerator. And we have d to the power 4. D to the power 4 is 75 to the power 4. So maximum bending stress here will be equal to 163. That will be megapascal. It's the same tension and compression on the top and bottom fiber. A beam A is simply supported at its end, carries a UDL of intensity W over its entire length. It is made up of a steel having a Young modulus equal to E. Beam B is a cantilever and carries a UDL of intensity W by 4 over its entire length. It is made up of a brass having a Young modulus is E by 2. The two beams are of the same length and they have same cross-sectional area. If sigma A and sigma B denote the maximum bending stress developed in the beam A and B respectively, then which one of the following is correct? He says that they are having the same cross section. Same cross section means they have the same circular section or the same rectangular section. In that case, the value of C is fixed for both. We know here that the maximum value of a bending stress sigma B maximum is same as equal to maximum bending moment M multiplied by C, that is the distance of a top fiber or bottom fiber which one is maximum, divided by moment of inertia I. Now C and I is same for both cases. It means that the value of sigma B maximum is proportional to the maximum value of bending moment. So you have to just find out here the maximum bending moment in the first case and the second case. In this case, the beam A is made up of a steel having Young modulus equal to E, and we have two support and we have UDL equal to W. So reaction in this case is same for both. Total downward force is W into L. So we have reaction is WL by 2, and this reaction is also equal to WL by 2. Maximum bending moment we can confirm from the shear force diagram. On the left support here, we have vertical upward force that equal to WL by 2. So at this end, you have to move vertically upward, and this value is same as WL by 2. There is a UDL is acting here, so you have to move downward. Total UDL is WL, and this load is WL by 2. WL by 2 minus WL. So at this point, we left here with shear force equal to minus WL by 2. If it is a rectangle in the load, then we will get a triangle in shear force diagram. So by symmetry exactly at the center, that equal to L by 2, you will get the shear force sign change. That is the shear force equal to 0. So left hand side shear force is positive, right hand side the shear force is negative. So there is a sign change. At this point here, C, we have a maximum value of bending moment. And this maximum value of bending moment can be obtained by the area of this triangle, or you can take the area of this triangle. So maximum bending moment will occur at point C. So we have MC is same as equal to the maximum bending moment MX is same as the area of the shear force diagram is 1 by 2 into W into L by 2 again multiplied by L by 2. So we have WL square by 8. So that is the maximum value of bending moment, WL square divided by 8. The beam B is a cantilever and carries a UDL of intensity W by 4 over its entire span, and it is made up of a brass having Young modulus equal to E by 2. So this one is beam B. This one is a cantilever of a span equal to L, and the UDL is W by 4. Now it is known here the maximum value of a bending moment always occur at the fixed support. Let's say the support is D. So to find out this value, we can convert the UDL into equivalent point load. So equivalent point load will be W into L by 4. We'll show here exactly at the center. This one is equivalent point load is WL divided by 4. And this load will act exactly at the halfway, that is L by 2. So maximum bending moment will occur at point D. So for second case, we have maximum bending moment at point D. will be equal to WL by 4 multiplied by L by 2. So we have WL by 4 multiplied by L by 2. That is same as equal to W into L square divided by 8. Now as far as the equation number 1 is considered, the bending stress is proportional to the maximum value. And in this case the maximum value is same, that is WL square in both the beam, that is beam A and beam B. It means that the bending stress at A and the bending stress at B will be same value. So we have sigma A by sigma B is same as equal to WL square by 8 divided by WL square divided by 8, that equal to 1. So both the beam have same value of bending stress. So in this case our choice A is correct choice. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.